I think we are recording. Yes. Okay. Um, Hello all, and welcome to the week 6 of your of this lecture series. Um, and we'll do today the assignment 5 questions. Hopefully, it wasn't that difficult, so we'll get through it fast, and then we'll move on to some ideas on neural networks and how to build them and stuff like that. Yeah. Um, Okay, so let's get started right away. Assignment 5, first question. Any doubts, any thoughts on this? People who have given the assignment, tell me what the answer is and why.
It is a linear, sir, because we can draw a line separating the two classes.
Right, and now we can simply draw a line which separates two classes, with the two classes, and the point is ideal complexity can be linear because there's only one point which is violating this particular rule, so we should be okay with that, right? That's the idea. Then second thing is, suppose we are doing a linear SVM classifier with two-class classification problem, and we have given some points which are support vectors, right? And if you remove any one of the red points from the data, will the decision boundary change? So is the answer yes or no? And why?
The answer is yes, sir.
Ah,
Because decision boundary is decided with equal margin between two different classes. So if we change any of those support vectors, then the decision boundary will vary.
will change. Correct. Yes. So at least in SVMs, the idea is that you can keep only the decision, only the support vectors, and because only they decide or they are involved in the decision boundary equation, line equation. So we don't need to keep any other points, but any of these are affected, the boundary will change. All right.
Sir, I have a question.
Go ahead.
Here, suppose we remove the red point, the -1, but still one of the support vector can still remain the same, right? Sorry, the decision boundary can remain the same. It's about calculating. Okay. No, can you just illustrate? For example, you remove that one particular red point.
Okay.
What could be the decision boundary? Say the choice varies.
Sure. Yes. So let's just do that here. 1 second. Yeah. Thinking. Okay. So yeah. So this is question 2, assignment 5. So currently, what do you think the decision boundary would be? Something like this, right? Something like this, right? Straight something, right? This would be the decision boundary now. But let's say if I were to remove this point, for example, right? Now, so then what will happen is the ideal or the best boundary could become something like this. Yeah, something like this, right? Where then what will happen is this will become a support vector. This might also become, and these two might become the support vectors, right? Something like this on these lines. So that's possible.
Okay, sir.
Sir, can we say that whenever there is a removal of the support vectors, always this boundary will change, or it is not always? We should see the. Can we do blind statement like that?
Yes, because so there is actually one particular case where it starts failing, this particular statement. So without complicating much of the idea, so I'll give you one thought process. So in soft margin SVM, right? Uh, so in soft margin SVM, the idea is, I mean, uh, you might encounter this somewhere in your life or whatever. So in soft margin SVM, there's a possibility that there are some points of the data which are exactly on the margin, right? But they don't but they don't affect your decision boundary. So I'll show you one example. Let's say this is the boundary, for example. This is a decision boundary, and let's say I do like this is a margin, yeah? Something like this. Yeah, okay, nice. This is the margin. Okay, now I have points which go like this, for example, and plus like this, right? So now what will happen is sometimes what can happen is if you remove this point, for example, it's possible that because of some other point which is already on this boundary. For example, let's say I draw one more point like this. Okay, so now what will happen is if I remove this point, though it is on the boundary, it still doesn't make a difference, right? So but there's one convention that we follow in that. The convention is if the point affects the boundary or affects the margin, affects the boundary in any way, only then it is called a support vector, and vice versa. So therefore, the blanket statement that you made is perfectly all right, not a problem. Okay, so if you tell that removing support vectors is double implies changing the boundary. So this is fine. In the case of SVMs, it is fine. All right.
So basically that extra redundant point will not be a support vector in that case.
Yes, so though it is lying on the margin, then that's very important to understand. Though it is lying on the margin, we don't consider it as support vector because its contribution towards the boundary calculation or boundary equation is zero.
So basically in this particular case, 3 crosses, any 2 will be the support vector.
Correct. Yes. Yeah. Okay, so this is the question 2. All right. Next, question 3. What do you mean by hard margin in SVM classification? So I guess A is what many of you should have answered. So any thoughts on, does anyone have any contention on this?
So I would like to qualify the statement like very low error in during training phase, I would say.
Correct.
Because it may not be in actual regularization time.
Yes, that is true. That is true. So see, that is true for any classifier, for example, because we can never know how it will work in the test data, right? And we make certain assumptions about the test data. Only then we can prove something about the classifier and all of that thing. So ideally, and I mean the word allows, that should give you a sort of a hint. We're talking about the training error classification, right? So we're talking about, so it allows very low error in training data classification. Test, we really cannot make that much of a blanket statement. That is true. All right. Okay. Question 4, linear regression, logistic regression. So very clearly, the idea is that linear regression models the relationship between input features and continuous target variables. Yes. So it's one of the possible models in which we assume a linear relationship. Linear relationship in parameters, actually, not just the target variables. And here and we use logistic regression because we want to model the probability of binary outcomes, right? So hopefully that is clear. Any thoughts, any doubts? No? Okay.
Sir, just to the previous question, the number 3. When it's say but very low, it's mean by the outlier, am I right? Because otherwise the hard margin is always the it is, you are able to see the clear classification, am I right? There's no vectors are there in the boundary, in the margin. That's called hard margin. So here the low error, otherwise it will be zero error. In the attempt is to do the zero error, am I right? Because it's clearly classified.
Yes.
The low error means the outlier. The outlier only here, the low error means it will allow the outliers only, not any other. Otherwise, That's what the difference between the soft and hard margin, am I right? That's what I got confused when saying low error here.
No, no, yes. So here low means zero error, correct. So see, uh, let's say the problem, whatever data you have is linearly separable. See, even if it is not in the current dimension that you have, let's say in some higher dimension also, if it's linearly separable, using kernel SCM or whatever, you can get the right boundary. But your point is right. So hard margin always tries to get perfect classification on the training data, right? So only soft SVM or soft margin SVM allows for your errors in training classification. So here very low error means zero error is what you can think. Yeah. Is that clear?
Yes, sir. Thank you.
Okay. Right. So that is then question 5. So after training an SVM, we can discard all examples which are not support vectors and can still classify new examples. Again, as we discussed just now, it is true, right? So only support vectors at the end, they make up the definition of your boundary, uh, define your boundary. Okay. Question 6. So suppose you're building a SVM on model on data X. The data X can be prone to error prone, which means you should not trust in any specific data point too much. And then you have some SVM quadratic kernel degree 2, all is fine. So the point here is we want to understand question 6 and 7. The idea is how does the value of C affect your SVM margin, right? So what happens when we have a large value of C? What would this mean and why? I mean, the answer is given, but what is the reasoning here? Any thoughts? So what does large value of C cause the SVM to do?
So when the C value is large, sir, the penalty or tolerance value will be small, or the regulation parameter will be small. So in that case, the model will be overfitting. So when it is overfitting, so it means that it can still classify the data correctly for any given data set.
For any given data set, yes. So let's say whatever data you give, that it'll try to classify. We don't know how it will perform on the outside. I mean, what is it called? The validation, all of that. But whatever data you give it for training, it'll be able to classify it almost
Uh,
correctly.
so basically, I mistook this question. Like I thought at test time, what will the date classification be? So with and since it's telling that training data has some outliers, you
Right.
can see
Uh,
it alludes to that it has outliers. So this class, I thought this question was like at regulation time, that is validation or test time, what would be at test time, if there are outliers and we are overfitting, then the data may not, that model may not hold good during test time. Uh, uh, so I think so. This question should have been written data correctly during training phase. Uh,
hmm.
uh, are you get? I
I
I took this
hmm.
as that the training data has some outliers. If we have C infinity, that means it will be a hard margin, right? Hard
Yes, it
margin, and
correct.
that means it will classify training data very correctly, but the model will go haywire and it will may not hold good for during test phase. I took it in that sense, but I think so answer is according to like during training accuracy, what will the data be basically?
Hmm.
So I felt question may clarity wasn't there. Uh,
So I think so. 2 points to make here. One was this like on data X. So we're just talking about one data set that we have X, and on that you want to do your SVM model, right? So I mean that's one, and the other thing is
no,
the
in data X2, if we divide it uh, and
right.
then during validation and test phase, it may go other way around. So that is what I felt. Somewhere it should have been written during training. Basically, C too high is also not good actually.
Correct.
It's prone to overfitting with outliers in the training time, and it is saying that the data set X has outliers.
Right.
So I don't know
Mm,
if you could write to them. I don't know. It
mm.
it may have some uh, clarification issue in this question.
Uh, sure. Let me ask them, but I think it's at least from my point, it's my perspective. It seems fairly this one because of the and also the way the options are given, right? We can still classify data correctly for a given setting of hyperparameter C. So the idea being that so the point is, let's say you have a lot of data, and some of it is error prone. So therefore, there are outliers. But the point being that, okay, if I use a large value of C, I will be able to classify the data correctly, which is completely true, right? Um, and vice versa here. So, but okay, I mean,
But
I
correctly also it means how much if it sees tending too high, then accuracy on the validation set or the test set may be
no,
affected. I don't know. Yeah, it's okay.
point on I got your point on the fact that yes, on validation and test data we'll not be able to make such a claim, but the idea is this that we're talking about just the given data X. So let me ask them, but I think let's see. I wouldn't hold out much hope, but let me ask them. Not a problem.
Sir,
Yeah.
sir, might be I can just provide my input because
Go ahead.
like when I was reading a question, I
Hmm.
felt like when it was like suppose you are building a SVM model, so you're
Hmm.
on data X. So I felt that whenever you are building a model, it will be on the training data. And again in the line number 3 also it said like now think that you want to build a SVM model which has a quadratic kernel. So might be that is why I thought it was on training data and I could select that answer.
Valid point. Yeah. So yeah, building a model can be construed as okay, by it's only on the training, and obviously testing would the building is not a part of. Uh but
Testing
when
means I thought like predicting, right, sir? Like they will ask like, okay, if it is predicting or something like
no,
that,
but
right?
I mean, I'll be a bit careful there because when you say hyperparameter, then building the model means tuning the hyperparameter also, which brings in validation set and which brings in Abhiroop's point of what would happen and all of that. Okay, but
Okay.
ठीक है, I get your point. Let me ask them. Yeah, we'll see. So but yeah, so I guess the overall idea is clear. If you use a large value of C, it means basically that we are giving that any sort of misclassification gets a very high penalty. So therefore the SVM model will try to fit the training data as well as possible, right? Even if the data is such that it is error prone, right? And therefore on point number 7, so question number 7, you can see the opposite will happen, right? So when you have very small C, you'll have misclassifications happening because then you allow for misclassification to happen. You allow some points to be misclassified just to make sure you don't overfit on the training data. So one second, my question for question understanding for questions is different as it it means you absolutely do not want any
Um,
misclassified.
Hello,
Uh,
can you hear me?
yes. Who is this? Go ahead.
This is Satyakant.
You go ahead. Go ahead. Yeah.
Yeah, I actually typed out my questions in the chat, in the text chat messages. Can you please go through that? That might
Yeah.
work
Yeah.
simpler. My mic is not too
That's
good.
exactly what I'm going through. Yeah. Yeah. Just as C nearly zero means equal misclassified points, can't we just test these scenarios in implementation of some channel? No, no. See, the point is not that. The point is we can obviously test out the scenarios. The point is on if your validation data or your test data is such that it doesn't follow the way your training data is, right, for whatever reason. So then that's the problem. And my point being that whatever you do at the end, you do not know what validation data or what test data is going to come, and therefore you cannot make any claim. So hopefully these things should be on the training data itself. So is that okay, SK? Yeah. All right.
The question 7, the multiple choice in question 7, C is equal to 0, misclassification would happen. The wording is very broad. Misclassification would always happen in many cases. I mean, what's so great about it? I mean, though I got everything is correct here, but nothing is crisp. You will never have a misclassification will not happen, means it'll be overfitted data, highly overfit data.
No, yeah, correct. No, but the point here is in contrast to question number 6, right? So again, see, the idea is how does the C parameter, the hyperparameter slack variable parameter, how does it affect your SVM's characteristic equations, right? So here the idea is if you have a large C, you will not you will have perfect sort of classification, and if you have if C is very small, then you'll have higher amount of misclassification or more misclassification than you would expect. That's the idea.
But if you have a large C, means you will have a near perfect classification. That's what you're saying.
Yes, near perfect classification. Because when you say large C, when C tends to infinity, it basically boils down to a hard margin classifier, right?
Yeah, that means the margin is very large.
Yes. No, margin very large. No, you will have misclassification 0. Margin may not be very large.
Okay. Okay.
Okay. So in this one, no, the what sir told, no, that that the misclassification happen. Like anyway, it will happen. That was the comment. But that question should be taken as no. They told it is more error is there. That means there are some errors in the boundary itself. From that point of view, this question is miscalculation is correct only, because they already given in the question there is a error is there. So hard margin is not possible at all. When you do the soft margin, when you give C equals 0, you are trying for hard margin, then misclassification will happen. Am I right? So that point of view, misclassification is okay. That word is okay. Since the questions given that it is not possible for hard margin, it is possible only the soft margin, and then you are trying for hard margin, misclassification will happen. Am I right?
Yes. Not trying for hard margin, trying for a very soft margin, basically.
Yeah,
Very
C equals 0. You are trying for both C equals 0, then you are allowing the misclassification, basically. Correct? No.
Right.
Hello again.
Yeah, go ahead, SK. Go ahead.
Right. So I typed another question, but I think I can speak now. The C equal to infinity case, doesn't that simply equate to the opposite of C equal to 0, where you're saying that in one case, no, you cannot, I mean, you can have any amount of misclassification, the points can be inside the margin, whereas that C tends to infinity, nothing can be in there. And because there are actually points which are going to land up there by the virtue of the nature of the training data, therefore you will never have a solution that's possible no matter what margin you try for, however many lines you try on the decision boundaries you shift around, and whatever, you are not going to find a solution. Isn't that what C tends to infinity means?
So C tends to infinity. We are not taking equal to infinity, right? So
No,
some
but
large value of C.
yeah, but I mean, in practice, tends to infinity would be dependent on context, and it could be 10 raised to 9, it could be 10 raised to 25, or it could be 10, just 100 or 10, depending on the data and the numbers actually involved. But when it tends over there, does it mean that just, I mean, literally being not infinity is going to still provide a solution? I mean, wouldn't you? I mean, isn't C in some sense like, say in optimization problems where we say that we want an error below 1% or 0.1% or something like that. The infinity tending it itself means that we are trying to achieve it. Like if you say we can get to 0.1, no, I want 0.001. Okay, 0.001, but no, you have to get it below 0.00001. Isn't that the sort of sense or the the implication of this C tends to infinity? The reason I ask is because I mean, to me it looks like we should be able to test this out with some kind of a test data and just run one simulation and find out whether as we keep increasing C we actually get a solution or not. Because to me it looked like both the extremes are not going to work. I marked, my answer was, I got 7 correct and 6 wrong because I marked it is not going to work in either case. And that I still feel is what is the correct answer. I'm not convinced that for C it would work at all.
You're not convinced for C equal to infinity it will work at all?
I don't think it will work at all. I mean, I don't think you'll find a solution at all when C tends to infinity, because it will say that you want something really perfect, but you cannot find it. So the simulation, the calculation engine is going to keep going around in circles and saying, no, not this, not this, not this, not this, not this. And it'll say it's never, what you want cannot be found. That's what I think is, I mean, I actually not run simulations. I think that's what I mean. My next step would in fact be to, get improve or do whatever in Python with the respective modules and, get some standard and unimpeachable test data and then keep increasing C in that and see what happens. Essentially some kind of, parabola kind of curve where, for the low end and the high end, you don't get accuracy, but in the middle, you'll find some solution with some tolerable error margins. That is the sense I have of this thing. I'm speaking intuitively. I don't have any mathematical proofs or any actual experience with the matter. So it's a question.
Again, see, the point here is we want to understand when the data is error prone. The idea is we plan to use slack variable. Now the point is, with this slack variable, can I make sure that I will be able to classify data? Yes, if I use a large value of C. Now I implore you to go ahead, try your simulations, and see the point of impeachable test data. You will never be able to prove it. From my experience, I'll tell you this. Okay, this is exactly why these questions are here, so that you can build some intuition around the problem, right? So let's say you know for a fact that the data is error prone, then using a hard margin SVM may not be the right approach. But you can use a soft margin SVM in case you want to have very good classification on your test on your trained data with a slack variable, and using a large value of C. We say that okay, try to get as much as right. That's the idea of saying a large value of C. On the
okay, but then okay, fine. Okay, in that sense, then I get the spirit of the question based on your latest explanation. But the question, as it was worded, does not then make a distinction between, say, an intermediate large values of C, whereas as opposed to say extremely pathologically large values of C. Does the question ignore that distinction? Like maybe you will find a solution for C equal to 10 raised to 5, but you would not find a solution for C equal to 10 raised to 10. Does this question cover that case or not cover that case?
No. So this is exactly the point. You cannot literally quantify any of these words that you're saying. Unpathologically large, all of these are not quantifiable words. So hence we just say very large value. That large value can be anything. And rightfully, as you pointed out, that C can be C equal to 100 may be a very large value for a given data set. All that is right. The point here is to build the intuition around what C is, what effect C will have on a noisy data with SVM.
Okay, fine. Okay, so now let me, should we say, restrict the scope of my question? Suppose we are working with a specific, a single example where we have a certain data with whatever properties, whatever scalings, and we do find that we're getting some kind of a solution for, let's say again, C equal to 100. Suppose the solution that we get at C equal to 100 may be acceptable, but if we keep going beyond C equal to 100 up to 10, C equal to 10 raised to 5.
Okay.
Then will we see a degradation in performance or will we not see a degradation in performance? That's my only question.
Correct. And that's exactly why we use validation set, right? Because all of this, and this we covered in the first class also. I told you about something called hyperparameter. So how do we know what value to set for that? Now the point is all these hyperparameters you tune using a validation set. So the idea is because we don't know how the model will perform on a test data, because by definition test data means something that hasn't existed yet. You don't have access to it, right? So therefore what you do is whatever training data you have, you break it down into a, let's say a sub, let's say training data and your validation data, and you use your validation data to as a proxy for your test data. And then you estimate, you get your performance of the trained model on the validation set to understand to get an estimate on how it will perform on some unknown data set. You will use all those sort of different validation splits and all of that to understand what's the right value of C. This right value is not the right value. It's an estimate of the right value of C. Always you will work with estimates. You don't have the true value that will work. And then whatever you have, that's the best you can do. So you will do that and you'll move ahead.
Okay. Well, again, I mean, I think I understand, and I completely agree with what I've understood from what you said, which is essentially that whether the training data represents the characteristics of the underlying distribution as represented through the validation data set and subsequently to the actual test data set. But I'm not focused on the case of a mismatch between the distribution characteristics of the training data and the true underlying real world data. My focus is on the value of C itself, given that the distribution parameters are accurately represented in the training data itself. In that case, what happens? If you find you have an acceptable solution at C, supposing it is working on the training data, on the validation data, and on the test data for a given value of C, and then you increase C by a factor of order of magnitude 5, 10, 15 something. Infinity, because 100 is not infinity, 10 raised to 2 is not infinity, 10 raised to 10 is also not infinity. Related to that, 10 raised to trillion would be infinity. So as you keep going beyond a working C, once it is working on everything and our test data itself is okay, then is it going to fail?
It will fail, because what will happen, it will start modeling the noise now, because whatever data you have, whatever, let's say you say it is accurately representing the population parameters or whatever, it's at the end a distribution. That means there is some noise associated with it. So when you have noisy data with you, whatever data you have is noisy. Let's work with that hypothesis. Right now, whenever you have the noisy data, if you increase C, it will start becoming bad.
So then does that mean that, does that not mean that, if you really start talking about tending to infinity as opposed to a sufficiently appropriate optimal value of C, which is large enough? This question is not distinguishing between those two cases, is my point.
So that's exactly the point that we were talking about before, saying that when you're saying the building on the data X, does it mean purely the training data, or does it include the idea of validation and test data also? Now, that is where I said, let me ask ahead and come back to you. But I don't think that this is something that can be, is arguable at that level.
Why not? Essentially, yeah, please.
So one second, SKC, I'll keep all these points. Let's see, what will happen. Is that fine?
Okay, fine.
Yeah.
Fine. And by the way, since I am on the mic, this is my first time attending your live session. So far, I only downloaded your sessions, and I had to install Microsoft Teams in order to speak to attend these sessions. Everything else I attended has been on Meet only. I think your sessions are very good, and which is why I think it'll be more productive to attend your sessions than the others.
Oh, thank you. Thanks a lot.
Yeah,
I'm glad it's useful. Yeah. Okay. Okay, good. So I'll now keep these points. Let's see, what the final outcome comes. Yeah.
Yeah, sure. Yeah, and the point of saying that was that, so far I've never had a chance to articulate my problems with the quizzes before this one as well. So at some point I might actually get back to you with my questions on previous quizzes, the ones which have been marked wrong.
Sure. Yes, please do that. So whatever doubts you have, go ahead. You can. There are also some people who have just, through the forum, they have sent a personal email also. So I've written that back to them also. Not a problem. So whatever doubts you have, go ahead and ask. And if I have if I have the right way to answer it, I'll answer it. Otherwise, we'll take it up and get a final answer from the the course TAs or the the teacher, so that that will be the final word. So then what needs to be understood is that the way we understand the question, that needs to change. So that will be the
yeah, but that can be a defense only provided the question has been articulated correctly. If there's a deficiency in the wording and it is ambiguous, or it leaves the possibilities or picks only one of them and expects us to be mind readers, so to speak, then that's not fair, is it?
Yes, sure. I get your point.
All right. Yeah. Thank
you. Okay, good enough. So then, eighth question. So I think we have the solution that has come out already. So I think this is just a very straightforward derivative, again, some high school 11th, 12th calculus. So I guess this should be straightforward. The idea is that if g of z is a sigmoid function, we can get the derivative with respect to z as the first expression, g of z into 1 minus g of z. All right. Then I hope no questions there. Then let's go to question 9. Again, same idea. So if you have a linearly non-separable case, what effect does C parameter have on the SVM mode or model? So it allows us to trade off the number of misclassified points in the training data and the size of the margin, right? This is exactly what C parameter will have an effect on, right? That's what we understand from the C parameter.
This will happen only even if it is a linearly separable case, right?
Linearly separable case. Yeah, if it's a linearly separable case, then C parameter will really not play any role anymore, because then what will happen is any value of C you use, you will still get perfect classification. So you will. So the idea is that the C parameter becomes useful when we have this sort of linearly non-separable case. But you're right. Uh, so there's no trade-off there anymore between number of misclassified points and all of that. But the idea is right. If it's linearly separable, then C parameter doesn't really have any effect. That's the idea that they're trying to bring out here.
But you can have a linearly separable case, but also noise. In that case, C will have some effect.
Yes, exactly. Yes, yes. Yes. So you're saying the linear separable case and
Noise.
noise.
He's
Uh,
telling linear, just like the first question he meant. First question, where it's more or less linearly separable, but a noise item is
but
there.
the noise is there, right? No,
Yeah,
but
yeah, yeah,
I
exactly.
think, I think what is another way of viewing this question could be something like this actually. So if you say something like this, right? Now this is linearly separable, we know. Now let's say due to noise, some point, so here in this case, my right classifier or could be something like this. Hoping this is right, right? And then let's say now because of the fact that your a noise, some point came up somewhere here, right? So then your maximum margin maximum margin classifier line boundary could come somewhere here then, right? So yeah, I'll have to think about that a bit actually, because if it's linearly separable, then C parameter. Mm,
Sir, I think the other way you can look into,
mm,
they're very close. That means no, the data is very, very close. Then C is playing much role. That's what I understood when I reading this. This is but if you're very close and it's not easily separable, or some noise also there, cross is there, then C is playing role.
right. So yeah. So what will happen is, I think you're right. Who said the person before? So the idea is correct. Yes. So
Bhushan.
if you have a Bhushan, yes. So linearly separable case also, but you have noise, then yes, C will affect your trade-off between these misclassified points, because then what will happen is, we're saying instead of fitting exactly to that noisy, this one, so we are looking for some sort of a trade-off between these two approaches. Okay, by trust the data completely, or it's okay, you misclassify some points, but give me a more robust solution. So yes, you're
Okay.
right. In linearly separable case with noisy, then C will still have an effect on this one. That's correct. Okay. Yeah. Question number 10. So what kind of kernel function is commonly used in nonlinear classification? Again, RBF kernel is generally used because of the fact, I mean, I hope you guys know why RBF kernel is important. Was this covered in the lectures?
Not very deeply. Could you just repeat?
Okay, fine. So just yeah, so this is actually interesting concept. I think you should be aware. It's a nice concept to know. So I think this is covered, right? So when we say kernel function, the idea is that it takes your data point, some x, into some space. Let's call it phi of x, right? And then it computes a dot product. So when I say dot product, we are looking at similarity between 2 points. That's the sort of intuition that we give for dot product, right? So let's say I have x, let's say I have y, and then what we do is this phi of x is also a vector. Phi of y is again a vector, a higher dimensional vector actually as compared to x. And there you compute this phi of x transpose phi of y. This is equal to the kernel function evaluated at x and y. Okay. So when we use RBF kernel, what ends up happening is you actually project this x into a infinite dimensional space, right? Infinite dimensional space. So what ends up happening is you actually can capture a lot more non-linearities with RBF kernel if they exist in the data which are useful. So hence RBF kernel is generally used in all your in many applications, because see, choosing which kernel to use now should I use quadratic kernel, should I use polynomial kernel, and so on, is a difficult choice to make. Ideally, what people do is they try different kernels and which one works best. That's how they move ahead. Now, instead, the idea is that when you use RBF kernel, because it goes to infinite dimensional space, the hope is that whatever the relevant features are there in that infinite dimensional space, they will sort of drive your solution towards drive your problem optimization towards the right solution. Now, why does it go to infinite dimensional space? All that if you want to understand, just try to expand this x minus y squared. I guess this is what the final formula is. We can just confirm this. What's the right formula here? Using a Taylor series expansion. Okay, so try doing this. You will get to know. You will get to know what this phi of x for this RBF kernel actually goes to an infinite dimensional space. And there you compute the dot product between the 2 points x and y. So, and again, you cannot actually go to infinite dimensional space on the computer, but the idea is that using a kernel, it allows you to bypass all of that and gives you a nice little computable, tractable way of getting this huge feature space from from a simple computation. Okay, that's the idea of kernels. Is what I said clear?
So it will take more training time, right, with respect to other kernels then?
Yes, it can take, because I mean, no. See, because but what are you doing at the end of the day, right? You're just doing x minus y squared e power that's it.
So
right?
basically the dot product will be now higher, since it's in higher dimension, that phi x will be bigger vector now.
Correct. But the thing is, you're not actually going to the high dimensional space. See, that's the beauty of kernels. If you think about it, when you want to do quadratic kernel, let's say x transpose y squared, right? So when you do this, this is equal to saying that x has to go into a space. I'm mapping x into a space of one. I think you'll get some x and root 2x or something like this. You'll get, right? And then and y also gets mapped into this space, a similar space. And then I'm doing this, a dot product in this space, in this three-dimensional space. Okay, let's say this is one single numbers, right? So in case, so the idea is that we will not go to this space. Rather, what we have computed is equivalent to doing that operation. Okay, so the idea is, if I compute this is equivalent to taking x and y into infinite dimensional space, computing the dot product there. That's the idea. Yeah.
In reality, the computation is kernel is making it lower.
Correct. Yes. So by doing this, you're actually
basically it's like doing that same thing with less computation with kernel, due to kernels, correct?
due to kernel.
Yeah.
Yes, that's the idea.
I just want to ask a question. Many a times there is a confusion between this mapping and kernel. Are they same or they're distinctly different?
I'm sorry, mapping
and kernel concept, is it the same or different?
No. Mapping is any function. So a function can be called a mapping, and mapping again, any function is a mapping. Mapping can be even more complex as compared to functions. Kernel is a specialized function which has this property that when you apply that on x and y, it's equivalent to doing a dot product between between those two elements in a higher space.
Okay, so it is a dot product of fx and fy into a higher space.
Yes,
but not in reality. Means
not in reality. So that's basically just the interpretation or the math that comes out of it is equivalent to doing that operation. Is that clear?
I had a hello.
Go ahead. Yeah.
Yeah, I have a question or a comment over here. The question asked, what is used for nonlinear systems? As in, what is the standard practice, or what actually happens? Now we have not having done any examples or any numericals or even having any, should we say, a comment from anywhere saying that these are preferred for these scenario, these are preferred for these domains, or anything of that nature. Your I mean, in fact, the answer to your first question is that everything that you said just now, explaining about why this, the lower dimensional, higher dimensional kernels, all of this, and the specific property that RBF itself is an infinite dimensional kernel.
Right.
None of this is in the lecture videos, and it is not in the lecture slides. There is one slide which shares exactly these four kernels, that yes, these four kernels exist and they are used. So my, should we say, criticism, complaint, and question is, how were we supposed to know the answer to this question? Because that is, I mean, should we have been reading Bishop and Mitchell and Tipshirani for the related content every single time, or are we supposed to do a Google search? And I'm saying this because this is actually maybe at least the second time this is happening. In the previous weeks, there was one question, if I remember, with regard to k-means clustering, and it asked what are the disadvantages, and one of the options over there was cold start, which was a correct answer, and it's a word that is not there anywhere in the lecture videos and in the slides. After the solutions released, I did one Google search, and the first top result that it shows you, it says yes, cold start is a problem with this. So someone had in fact posted this on the forum as well, where is the word cold start mentioned. That was not me, it was someone else. So my problem really with regard to should we say industry practices or heuristics such as this is, how are we even supposed to know? The knowledge is edifying, it's all very fulfilling to listen and to do, but for should we say exam situations, etc., the kind of confusion that this kind of thing shows, and uncertainty it induces about whether we really know the stuff and are we doing this right, is kind of a little jarring.
Sir, I also agree. For example, the question is a non-linear kernel. So polynomial also non-linear and quadratic also non-linear. So then if it is not useful, then why are we studying them?
No. I mean, they didn't ask which kernels are non-linear kernels. They are asking for non-linear classification.
Yes, and non-linear classification only.
Yeah. No. So, so the question is, what is commonly used? The commonly used is RBF kernel because of this precise reason that whenever you they go to infinite dimensional space, so you have a large, a more richer, a way of getting your what do you call that? Feature extractors. But okay, if it is not clearly mentioned in the lecture notes and all, let me get clarity on that. Yeah, not a problem. Okay,
sir. Sorry to interrupt and come in between. In week number 4, when we are talking of probability, we have given a lot of numerical problems where it was really good for us so that we can take a pen and work out. But this is a week when I'm answering it, I did Google search and I'm able to get answers. You after 1 month you come and ask me, again I scratch my head. So, but the 4th week's questions are such that even if you ask me after 1 year, I'll be able to solve them. Now I'm in a discussion where I cannot understand anything. So I would request, there are 3 TAs for this course. Instead of questions like this, working on introduction to machine learning means they should be good in Python. So kindly create some Python questions so that we can practice and answer them. It's a request from my side. There is no point. Definitely, you ask me after 1 month.
So one second, I'll have to cut you off, Kamlakar. So one second. So again, I understand the point that yes. Again, this is your personal opinion.
Right.
Some people prefer things like hardcore math. Some people don't prefer that. So it is
50-50.
It is not the, I mean, we cannot cater to one particular way of solving. Point number one. Point number
50-50.
two.
50-50.
Again, so again, so the idea here is because this is I mean, again, ma'am's course. The idea being that intro to ML, the idea is at least if you're able to get some sort of intuition of how the things work. It may not be exactly precisely the mathematical things that go behind it, and
I
I'll be
understand.
I'll be very honest with you. SVM itself you can cover for at least 3 weeks.
I
There's so
understand.
much math in it. There is so much probability in it. You will get tired of, as you said, you want to take a pen and start solving. You'll get tired of taking your pen up. You have no idea. So the point here is, because it's an intro to ML course, the idea is you are being exposed to a lot of different algorithms, right? In a very short amount of time. So you're studying SVM, you're studying linear regression, you're studying unsupervised learning, you're studying, for example, let's say this week we have neural networks. The idea being that if you're exposed to different things, you can and because you know that something like this exists, you can take up, your next step could be, okay, I like this particular concept. I think I want to go something deeper in this. So then we have different courses available in the world, right? That you can, go ahead and learn more from them. So again, see, the idea here is we will have to keep a sort of content which is amenable to everyone, right? That being said, in Bayesian networks, as we discussed, yes, there are a lot of problems which were given, which are probability based, because there's not much to be, I mean, at least from my perspective, there's not much to be thought through there. It's very mathematical. SVMs is not like that. You have, because you can actually build a lot of intuition around SVMs. So without how SVMs work, you can still work on those intuitions. That's the idea, Kamlakar. So I understand your. So I would say, if you are really interested in doing something like that, go ahead. We have many multiple courses available in the world. Go ahead, take one topic, and do like a proper thorough analysis of it. But this course, again, as I said, it's designed by ma'am, and it's her choice at the end of the day. So this is how I would think why this is done this way. But if you have any general feedback, I think there is a feedback level, something that feedback form is being given. So feel free to give that, and she'll take up the ideas in the next offering of the course. Is that clear?
Okay. Yeah, I actually would like to make a comment here. Hello.
Go ahead.
Yeah. On the same point from the previous speaker, Kamlakar, if I'm not wrong, there's one course, NPTEL course I'm taking this semester called Cloud Computing, and it's all only based on the slides. As in, you do one Control F inside the PDFs provided as a lecture material, and you get answers to all the questions. The subject is purely descriptive. The instructor simply reads the slides on the screen, and there's, I mean, very little numericals, nothing, but it is just descriptive and remember. Not even, I mean, not even understanding demanded. On the other hand, and relevant to this course, or sort of a course, there is last term I had taken two NPTEL courses, Data Science for Engineers and Python for Data Science, which are very similar to this in structure. Python for Data Science is a 4-week course. Data Science for Engineers is an 8-week course. Both have tutorial sessions by TAs. There are Python implementations like this course has in the videos. The difference, what was there and is not here, and I think is a single point of change which can be implemented in the next round of the course, probably not in this run, is that you provide one standard data set, something about cars in the US or iris flowers data set, and you are told, run these 3 or 4 simulations on this and find out what the answers are for these numbers. Like, for example, for this value of C, that value of C, what are the answers you get? What it does is that it forces the student to go and do those simulations, and then we learn by doing and understanding and experimenting and playing around, not on pen and paper, but on Python. And that gives us a sense of what's actually happening, as opposed to the lecture slides said this, the instructor's voice in the video said this, and therefore trying to remember that like a descriptive thing in the cloud computing course. So that I think is a change which could easily be made, and which in fact is, I mean, I would have expected it by default in this course, but that's just a point, a comment. It's not, a question really.
Sure. So, feel free to add all of this in the feedback forms that have been given. So if, the instructor feels that this is something that will add a huge value to the course, she'll go ahead and do it. But at the end of the day, it's her call. Right? So
Indeed.
yeah. Okay. Coming back to the question, question 11. So again, things about kernel. The idea is that what is true about kernel in SVM? Both points are true, as we discussed. Kernel functions map the low dimensional data to high dimensional space, and it's a similarity function, as we said, because we said it does a dot product in that space, and dot product is basically generally included as a similarity measure. So that's the idea. So both 1 and 2 are true. That is C. C is the answer. All right. Then question 12. So the soft margin is preferred over hard margin when? So again, I guess we have discussed this multiple times now. That is, one is the data is noisy. Yes, because hard margin will try to find the without any penalty. Whereas if data is noisy, it's good to have some sort of a understanding of that particular factor also. And the data contains overlapping points. So again, very clean. You will not have a hard margin solution if the data have overlapping points. So therefore, in such case, soft margin SEM would be a better choice. All right. Then question number 13. Consider data points in the figure below. Again, so the idea is we have three boundaries which are being drawn here, right? One is green, blue, and red. So the idea is which one could represent the maximum margin classifier. So very clearly, again, H1 is misclassifying the points in the first place, and this you can very clearly see. Like for example, if you consider this side to be black and this side to be white, then it's strongly classifying these, and the other way, then it will classify all of these as wrong, right? But and H2 classifies them correctly, but very clearly it is not the maximum margin classifier. Rather, this could be the best answer. So from among these, we are asking what's the maximum margin class hyperplane. So ST seems to be the right answer. All right. Then yeah, so what is the primary advantage of kernel SVM compared to traditional SVM with a linear kernel? So I hope this is again clear. The idea is that it can capture non-linear relationship between the data points. So as I said about the RBF and even other kernels, the idea being that it projects to a higher dimensional space. So where you have much more richer representation of the same feature vector, and therefore you can capture any non-linear relationships in the data. All right. And
what is this linear kernel? Linear kernel is same thing like a simple linear separability, right?
Correct.
So there is no dot product involved in this.
There's no dot product. No. So because when you see the dual formulation, so there you will see that x transpose x. That's just linear x transpose y or something like that. So that's basically linear kernel. That's
okay.
it. Yeah. So linear.
Because I thought there's something more than just x transpose y. Something more than that is called a linear kernel.
Yes, exactly. Yes. Yeah.
Okay.
Yeah, correct. So yeah, linear kernel would be just your x transpose y, for example, right? Usual whatever feature space you have your data in, just compute the dot product. That's the linear kernel. In case you have anything different, for example, squaring of it, or all etc. stuff, that all becomes your non-linear kernels. All right. That is question.
So that clarification.
Go ahead.
You see? There is a traditional SVM. Okay.
Yeah.
Can you level it actually? This see, for example, in SVM we have the hard margin, then we have the soft margin concept, and then we have the SVM kernel concept. Okay. So
Right.
when you're telling a traditional SVM, it is always with the linear kernel. First level. Inbuilt.
Yeah.
It's inbuilt.
Yes. So when it's a traditional SVM, it generally means with the linear kernel. That's true. Just a moment. Yeah.
Yeah. That means.
Yeah. Yeah. Go ahead. Yeah. You were saying.
So if I reframe this question, removing the last the three words with a linear kernel, the answer is same only. Am I right?
Yes, it's same only. That's correct. Yeah.
Only the linear kernel word is rather confusing. We thought we had made something.
No. So traditional SVM generally, so traditional SVM means linear kernel, and yeah, so soft or hard depends again on the problem at hand. But when you say traditional SVM, at least the kernel function is thought to be linear kernel. That's true.
Can you say an example for SVM? An example for SVM.
I'm sorry?
Can you say some real-time example where we substitute the SVM concept?
Where we substitute with SVM.
SVM.
I mean, so basically any classification problem that you have in the have at hand, right? For example, let's say you have uh, um, a brain scan, for example, and you want to know whether the person has tumor or not, right? From the brain scan, that becomes a classification problem. So now you can solve that problem in multiple different ways. One way that you've already seen is, for example, logistic regression. One other way is SVM, and then probably this week you will see about neural networks, right? So that's a real world example where this becomes a very valuable thing also to have.
Sir,
Okay.
sir, in fact, as our colleague said, SVM with a linear kernel is an oxymoron. Just as SVM by default, without any prefix suffix, implies the decision boundary is linear. The moment you include kernel, that means it is a non-linear separating, right? Am I correct?
Yeah. So again, not separating. The idea is kernel dot product in a higher dimension space. So we're looking at nonlinear relationships in the data. But yes, you're true. If I just mention, if I come and say the word SVM to you, the first thing, I mean, the filters that you should have is yes, linear kernel, and generally also speaking, hard margin. If somebody mentions soft margin SVM, then it's SVM, and that's how we take it generally. At least I take it. So
okay,
go ahead. Yeah. So Gandhimati, is that clear?
Sir,
Example?
as you classification problem goes under the SVM, so automatically supervised data will be supported for the SVM concept. Is it so, sir?
Yeah, so because all of these what you looked at algorithms correct till now, they're all supervised learning algorithms. So yes, you need some supervised data. So you will have some labels saying, okay, this brain scan has tumor, this brain scan doesn't have tumor, and all of that. For example, let's say from some doctor who has given me all of the data. Then what I do is I build a SVM model on that, or I build a network model on that, and stuff like that. Yes.
As you say, kernel SVM goes for the nonlinear process. Will it support for the classification or regression?
No, see, okay, so I guess that's something that is not clear then. So 1 second. Okay. See, SVM as such is used only for classification, and even especially binary. If you want to do anything else, you need to do versions of this one versus one and all of those sort of things. Okay. Now the point is, where is this kernel thing coming into picture? Let's say if I have, for example, let's say 2 points like this, right? And I want to classify these 2 points. Okay. Now the point is I can either do it in this space itself, right? For example, let's say x and y space. No, sorry, x and y space. Or what I can do is I can go to a high dimensional space. Let's say I'll call it x, y, and z space. Okay. And I will mark this point x somewhere here, dot somewhere here, and then I will draw hyperplane here. Okay. Now the point is, this is where the kernel idea is coming in. The task is still the same. The task is you want to solve the classification problem. You want to know whether a point belongs to one class versus the other. The advantage of using kernels is that you can get that sort of a classification at a higher level without even going to that space. That's the idea of kernel. That's the advantage of using kernels. So you can capture any very complex relationships, right? And we'll actually do an example today if we have time, which will show you where one particular example of this, and their classification doing in that space might be easier than doing it in the original space that is given to you. Okay, so SVM is for classification. That much should be very clear. Gandhimati, is that okay?
Yes, sir. Clear. So when we go with the complexity, we proceed with the kernel.
Yes. So if you want to capture more complex factors in the data, then you try to use kernels. Yes. because of multiple reasons, as we saw, data could be noisy. It's not linearly separable itself in the first place. Those sort of things, and we'll see one example today. So,
Sir, practically,
Sir,
value how it will be.
I'm sorry.
Practically, the kernel value how it will be represented.
How it will be represented? Okay.
Of the classification goes on, we go with the kernel SVM. You say I can understand. Practically, the kernel value will be represented when we go with the complex classification.
Correct. Yes. So you want to know what k of x comma y gives you? Is that the question?
Yes, sir.
Okay. So let's say if x is, for example, a vector 1, 2, and 3, y is a vector, let's say 2, 3, 4. What will x transpose y give you?
1, 2, 3.
Dot product.
Sorry. Or let me make it a simpler thing. No. 1, 1, 1, 1, 1, 1. Yeah. What will x transpose y be?
3.
X transpose a 3. Yes.
Right. Just transpose this and do a matrix multiplication. Simple vector multiplication, right? So x transpose y is going to be 3. That's it. So kernel is going to give you this number 3, but at a higher level. But by taking this x and y to a different space, doing this dot product there, and then coming back and giving you this number. It will give you one number.
Okay.
Yeah. So if I say for one second, Krishna. So if you say, for example, let's say k of x comma y is, let's say, x transpose y squared, then this becomes 9. Okay, this is a quadratic kernel. Yes, go ahead, Krishna. Go ahead.
Yeah, sir. Just to confirm my understanding, that that decision boundary, whether without kernel or with kernel, it is always a plane, the one-dimensional, two-dimensional plane, or a hyperplane. But the data, which was originally not linearly separable, it becomes linearly separable when you are using a kernel function. Correct?
Yes. Good.
So the decision boundary is always a linear only. Hyperplane. Hyperplane also is linear, right? Right.
Yes. So basically, when you do this in the kernel SVM, the idea is you have gone from, let's say x is in Rn space. I hope so. Rn space means n-dimensional real vector. Now let's say using kernel you went to a Rm space, right? Let's say phi of x is in Rm space. Let's say m greater than n. So the idea is your decision boundary is now linear in this Rm space. It's a hyperplane in the Rm space.
Yes, yes.
And it will have corresponding representation in Rn space, but getting the corresponding representation is very difficult. There are multiple issues there. Let's not go there. But the idea is in this Rm space, it's a hyperplane. That's correct. Linear.
It has to be linear in the Rm space, you're saying.
Yes. Linear.
And you have to choose your kernel function appropriately so that it becomes linear in the Rm space.
Perfect. Yes. Perfect.
And if we are not able to find such a function, then do we increase the value of m or something?
Yes. So we can try more complex kernels. So I mean, m increasing is not in the hand. In the sense, we need to change phi. We need to change different. We need to try different kernels. Hence, the idea is we use RBF kernels because it takes into R infinity space. Now the point is in the infinite space, hopefully there'll be some factors, some features there which will make the the data linearly separable, and hence we prefer RBF kernels.
Just a little clarification of this term space. A two-dimensional space is nothing else but a two by one, that is two rows and one column matrix, right? Vector.
So two-dimensional space means a plane, a paper in your the surface of a paper or your laptop, your mobile screen. That's two-dimensional space. That's it.
Yeah, but that is how it's. How do you put it in vector? Vector is what? 2 by 1.
2 by 1. Correct. So let's say
and 3 by 1 is a three-dimensional space.
Yes.
And therefore n by 1 will be an n-dimensional space.
Yes, correct.
Okay.
Yeah, this is an n-dimensional vector, and therefore it lies in an n-dimensional space.
Okay. And the properties of transforming from 2 to 3 hold the same from n to n plus 1. ऐसा ही कुछ है, something of the sort. Higher dimensional space, all the properties are similar.
What properties are you talking about?
Like for example, say you can say in a 2-dimensional space, the Pythagoras theorem will hold true. In a 3-dimensional space also, it can hold true, provided you take the what you call a square plus b square and c square is the hypotenuse, and you take one z axis. That will be what will happen in something like an n-dimensional space. Something.
Right. I mean, yeah, there should be a equivalent version of that, but again, I'm not aware. So
Okay.
But yes. I mean, you will have some version of that happening in high dimensional space.
So for our purpose, the word space means a n-dimensional space means n-dimensional vector with n rows and 1 column.
Yes, correct.
Okay.
You can take it other way also. Columns
Pardon?
also. Columns also is another representation. There is nothing special. Row
Okay,
or
column. A column means you're saying that
one row means
one row and
row
5 columns. 1 row and n columns.
Yeah, it's your representation. How you want to represent.
Okay. ठीक है.
Sir, normally vectors we represent as columns, column vector, correct? By default.
Yeah, generally.
That's why we take transpose when you multiply.
Exactly. So yeah. So I mean, general convention that again it's a convention. So the idea is, I mean, at least I feel very comfortable working with a column vector. So if n number of rows, 1 column, that's how I have always visualized. Abhirup is right. It's just a convention matter. So some people again do this sort of a thing also, where they look at a row vector as the representation for a vector in some whatever space, right? So, but yes, this is what I feel comfortable with, and you will see a lot of books following this convention. Okay.
Hello.
Go ahead. Yeah.
Yeah, a few minutes ago on this writing surface that you are using, you wrote x transpose y the whole square and said that it is the quadratic kernel. Now my question is the quadratic kernel? Yeah, right. The x transpose y the whole square, is this the quadratic kernel, or is 1 plus x transpose y the whole square the quadratic kernel? Because that is the formula given in the wherever the quadratic kernels, polynomial kernels, 1 plus x transpose x or phi transpose phi, the whole raised to k is the k or p. P is the thing. So that plus is the plus 1 dispensable, or is it actually mandatory? Because once you have the 1 plus x phi transpose phi the whole raised to p or k or whatever for the k order kernel, then when you expand that, then you're getting the choice of those variables 1 at a time, 2 at a time, squares, cubes, and so on, and that is what gives you the higher order, however, the k dimensional space at the end. So is the 1 plus necessary or not necessary for polynomial kernel?
No. So I would say always keep the 1 plus with it, because that'll take all the factors involved in
exactly.
it.
Yeah, that was my question.
One variable, one all of that commercial will be taken care. Yeah. So here in this case it would be what 4 square 16 something. Yeah. So this is you're right. So quadratic kernel will be 1 plus this one power d. That's a d dimensional polynomial kernel. All right.
Yeah.
Yeah. So any other doubts on this question? Once again, what Jitendra clarify question 3 again. So I'll say, let's keep it for a while. We'll come back to it if you have time. Yeah. And last question, I guess.
Sir, yeah, sir. One similar question related to kernel, but similar concept. Here in kernel, we are moving from a low dimension to higher dimensional space to separate data, basically to classify data linearly. Okay. A similar concept in principal component analysis. Sometimes we do reverse. A multi-dimensional higher dimension to lower dimension, you transform the data.
Right.
Okay. Is exactly opposite there, right? In principal component, we have.
I got your point. Yeah. So yes. So in principal component analysis, we are trying to solve 2 problems. One is because we have high dimensional data, right? high dimensional data, there are some algorithms of machine learning which don't work well in this high dimensional regime of work, regime of data. So the idea is I want to reduce the dimensionality, right? So I want to reduce the dimension of the same data. Now, this is one point. Second point is that in this reduced dimension, I want orthogonality also involved in it, right? For example, let's say the different dimensions that I have should not be dependent on each other or stuff like that. Then there's another. So then the question comes, okay, how do I achieve this? So one way of doing it is you say I will take those dimensions which capture maximum variance of the data. That's how you bring it. So the kind of question that we're asking are two different. But you're right, in kernels, we're going from lower dimensional to higher dimensional for the purpose that I want to classify the data. In PCA, the idea is that I want to apply not SVM. I don't want to use kernels, but the idea is I want to use some other algorithm which doesn't work very well with high dimensional data. So then what to do? So PCA gives you one way of doing this, that is take a high dimensional data to a lower dimensional data using this approach, where you capture maximum variance in these dimensions. Is that clear?
One delta, this Bhushan is PCA is unsupervised thing. The other way, that is supervised. So this is just to reduce the dimensions so that your computational time will be less or model requires less dimension. That's it. Means one is unsupervised PCA. So it's just a we do PCA just before putting it into the actual model, the data. We do that.
Right.
It's not a PCA is just to pre-process the data before actually modeling it.
Yes, right, precisely. Yeah. Any other doubts?
Not a doubt, but I mean, what do you say? My understanding of the PCA versus SVM question, the objective in both cases is to not compromise on accuracy of results while reducing computations. Which one will work will depend upon the characteristics your data has. If it happens that it has less variance along or more variance along specific directions and less along others, then you achieve this objective by using PCA. Whereas if it is not linearly separable in the lower dimensions, but linearly separable in the higher dimensions, then you would use SVM. So it is a data that is given to you that's going to dictate whether you'll use PCA or SVM or for that matter, both.
Right.
So PCA is, I will not say data means PCA is not a modeling decision or classifier. It's just a preprocessor to your classifier. So it's not classifying your data. It's just reducing the dimension. After that, you're giving it to the model to classify. So PCA is not classifying any data. So PCA is just capturing the information content in lower dimension.
Yes. So PCA is only PCA again, as he mentioned, it's just unsupervised learning. So there's nothing there's nothing about the class labels, etc. Unlike SVM, which is a supervised learning algorithm, there you have labels and everything. You need to train the model. You need to learn something from the data to be able to classify it well. Here, the idea is that we are not trying to classify anything. In PCA, it's just about making the dimensionality reduction. One approach for that is that you capture maximum variance. That is the approach used by PCA. Is that clear? It's actually, so comparing SVM and PCA is like comparing apples and oranges. They are not comparable, but yes, there is one distinction that in kernels when we go from lower dimensional to higher dimensional, and that too that is not happening while computing. No, that's the mathematical equivalent of what we are doing when we use kernel function. Again, as I mentioned, right? So but in PCA, the idea is yes, we want to go from high dimensional to lower dimensional. Last question, I guess, should be clear. What's the function? What's the sigmoid function's role in logistic regression? So the idea is that yes, we want to capture, we want to map features to a probability value at the end of the day, because a sigmoid function is between 0 and 1. Its range being between 0 and 1. It's very clean and amenable to this particular, way of solving things. All right. So any doubts, overall doubts on the assignment 5 questions? Okay, so we'll move to the this is what this yeah, fine. Yeah, so we'll go to this one thing that I wanted to just make you aware of. So yeah, so there was an example of XOR that we had in the lecture slides, right? So let me just frame it again. Let's say I have this X and Y. So this is the classification problem that I'm trying to solve, right? So this is 1, 1. This is minus 1, 1, 1, minus 1, and minus 1, comma, minus 1. Okay, so as we can see, so this is one class, the plus class, and the circle the dot class. So as we see, we don't have any linear way of solving it, right? So one idea that again this is the general intuition that is given for learning, going above perceptron sort of thought process, right? So where we say that okay, perceptrons can learn linear boundaries, but if you were to use multiple perceptrons as such, they can learn even more complex boundaries, and they show that you can solve using a simple 2-layer perceptron, you can solve this problem. Now, can you solve this problem with SVM though? Because we know SVMs with kernels, they can they can go to higher dimensional and try to solve any non-linearly separable in this or in the original space. So any thoughts that you get when you see this problem? What kernel function you could use, or what mapping could you use to make this problem linearly separable? Any thoughts on that?
RBF will be able to do
Sir,
it. One of the figure in the slides looks like this similar.
I would do x plus y mod of x plus y.
X plus y mod. Okay.
I can think of squaring. So whenever I square, then 1 1 and minus 1 square squaring of x and y, x y square,
X y
x
squared.
yeah.
So this will be always one.
This
will be always one for all. How will you classify?
Or sorry, x y, just x y, x into y, not x y square. Sorry, yeah.
X into y is fine. Yeah, correct.
So x y, right? So this is a so we know what type of kernel is this?
Hyperbola?
That is a polynomial kernel.
Not exactly polynomial kernel also actually. So
Is it a hyperbola?
no, I think I have to think about that. But no, okay. But you got the idea. So what are we trying to do? We're taking a function actually. Not even the kernel will be difficult to define here. Leave that. So the idea is I'm moving from a XY space, right, to some other space, which is, let's say, X, Y, and XY space, like this, something like this, right? So I'm going from R square space to R cubed, right? And in that space, for example, now what will happen is I'll have, let's say, these 1, 1 would, let's say this is X, Y, and Z. So 1, 1, and then 1 into 1. So it'll come somewhere here out of this particular plane, right? Something like this here, right? And these points will be 1 minus 1, but on that side of the z axis, right? It's difficult to draw this here. So let's say positive z value right? Positive 1, negative 1 z value. And similarly, this will also come on the positive side, but lower. And this will come on the negative side, right? And then you can draw a linear function along this line, right? That's the idea. I'll give you one more example of this function mapping.
Circle.
Yeah, just a moment. Is something that like this, right? So let's say this and this. This is just x. There's only x here. Let's say, okay, x-axis, and now I want to classify these 2 points. As you can see, there is no linear system that I can do. So what any example kernel that you any example transformation that you would do to solve this problem? Let's say this is 0, 1, and -1. Any thoughts?
Just a square it now.
Just a square, right?
Square.
So I can take x2, let's say x and x squared, right? This is the mapping that I want to use. So then what will happen? I'll have x here. This will be the x squared axis, right? So 0, 0 will be 1, 1 here, -1, comma 1 here, right? This is the second point, and therefore I can draw some linear point here, right? So this is exactly what I was saying. I think Gandhimati, you were asking a question, right?
Sir?
Who has mic on? 1 second. Yeah, go ahead. Who had a question? Go ahead. Yeah, no. So I was saying that these are some examples where you can see that having like using a kernel makes it amenable to solving it in a high dimensional space. All right. This is the idea.
Okay, sir. Noted.
Sir, there's a more. I think we are not really going to higher dimensional. With
Yes.
the same dimensional doing the mathematical functionality without going, we are solving. That's the beauty of the kernel function.
Correct. Yes, because the kernel functions have such properties. So instead of going actually to the high dimensional, which we don't want to do also because it's just too much computation, but kernel functions allow us to do the dot product in that high dimensional space at a lower computational cost. All right. Okay. This I just want to mention XOR with SVM was NN. One thing that I wanted to, so has ma'am shown anything on how to do classification using using neural networks?
Sir, in neural network regarding the perceptron she has discussed and with the multi-layer, not the classification.
Not classification. So yeah, okay. So again, the idea is similar to how we're doing logistic regression. The idea is if you have multiple, let's say, layers and nodes of your neural network, right? What you do is you have some output node, right? That output node, just like in logistic regression, we pass it through a sigmoid function, right? This will give you the probabilities. At least we consider it to be the probability of belonging to one class versus the other, right? And then this is used to check whether the output is what we expected it to be or not, and then we get the error signal. So any thoughts what you would use to convey the error signal here? I mean, it may not be very clear right away, but can you use MSE sort of thing here? Because if I'm not wrong, for regression, see, for regression, we use this mean squared error, right? Now for classification, what will you use in this case?
It's like how far we are away from 1 or 0,
right,
after the sigmoid function.
Right. So how will you quantify that? Using MSE?
That is like output of sigmoid function. 1 minus that mod or something. I'm just thinking 1 second. If it's above 0.5, then 1 minus that squared, and if it's below 0.5, that minus 0 square. So it's basically delta from 1 or 0, that distance square.
So yeah, so that's one possibility, but that's not generally shown to be very well working in practice. So I'm not sure is it covered or not. So there's something called as binary cross entropy loss. Is this word
No, sir, I don't remember covering, but can you explain, sir, about this?
right?
Sir, as
So
you say, one of logical functions when we use either AND gates or OR gates, we go for the classification. Is it so? In that basis, you are discussing, sir?
see the and I talked about the and or examples in the lectures.
Sir,
Sorry.
in the tutorials we had some concepts regarding to that AND gates and OR gates representing in this perceptron part, and they discussed on it. Based on that, can we go for the classification?
So that's the intuition to build basically. So we're saying that if you have a problem like and sort of problem where you want to classify between two classes, right? 3 points are in one side, 1 point is in the other. That's an example of a classification task. But we already know classification is not just and or, right? We just now we discussed the example of brain scans, for example, right? Tumor, not tumor. Any classification problem that you have. For that we are discussing currently, right? So let's say you built a neural network, right? And you want to use neural networks to do this classification job for you, right? Now the question remains, because neural networks require this sort of error signal to train itself, right? In case of regression, we had something like a squared error. You are doing like y target minus whatever the output was of the network squaring and all of that. You were taking this derivative with respect to some weights of f of x and all of that, right? And then you had those nice little update equations for each weight. All of that you had. Now the question is, let's say in classification tasks, when you want to do, what is the error signal that you will use? So one approach for that is binary cross entropy loss, right? So where the idea is you do something like this: y into log f of x. Keep forgetting the formula. So y into log y hat plus minus y into log 1 minus y hat. Yeah, this should be the one. Yeah. Okay. So as you were saying, Abhirup, see, you were trying to do that. If something
It's
more
similar to this,
right. Right. So something is more than, let's say, 0.5, less than 0.5, that sort of thing is captured here. So here the idea is, let's say this is the target variable, right? Now the target variable in a binary classification problem is always 1 or a 0, right? So the point is, let's say if it is 1, then this part of the net, loss will get active and be used to.
Exactly. It's coming similar what I was trying to tell. Yeah.
Right.
Yeah, one.
So when it is 1, we're trying to say, okay, use the you have a minus sign actually in the beginning. All of okay. So let's say you have like this. So when it is 1, only this part of the loss function is sort of active and basically gets affects your error function. And when y is let's say 1,
Then the first
y is 0, but
gets
y
activated.
this is not active, only this part is active, right? So we are saying, so what are we saying then? Let's say y is 1, right? Then my loss is minus log y hat. Okay, this is my loss value. Now when y is 0, my loss is minus log of 1 minus y hat. This is my loss. Okay, so what are we saying? We're saying when y is 1, you have to minimize the loss. We know that, right? Always loss has to be minimized. Now, when you're trying to minimize minus log y hat, what does it mean in terms of so minimizing minus log y hat means maximizing log y hat. I guess this is, hopefully you're clear on this. Now we know that log is a monotonic function, right? Monotonic function. So maximizing log y hat means maximizing y hat. So what are we saying? So y hat is what? Y hat is the output of this network. Whatever after applying sigmoid, let's say after applying sigmoid, what is the output, right? So we are saying whenever the target is 1, try to maximize your output. Try to make it as close to 1 as possible, because y hat will also be between 0 and 1. After all, y hat is also a probability value, right? Because we're saying we're applying sigmoid on the output. So we're saying maximize y hat as much as possible. So the error signal that is there for the model is this. This is the error signal. And how does the error signal help the model? Because it is minimizing this is equivalent to saying maximize is y hat, such that and because y hat will be only between 0 and 1, make it as close to 1 as possible. Similar thought process you can use here. So minimizing minus log of 1 minus y hat is equal to maximizing log of 1 minus y hat, which is equal to maximizing 1 minus y hat. Why? Because log is a monotonic function. This means it's equal to minimizing y hat. So we are saying whenever y is 0, make y hat as low as possible. And because y hat is bounded between 0 and 1, it tries to make the value as close to 0. Is this clear?
Yes, sir.
Sir, yeah, sir. This derivation was explained in the logistic regression for the sigmoid function, basically. But that word is not used. That whatever word used now, binary, that word is not used.
Fine.
And
That's
she
what I-
explains then again she explains sigmoid function in here also for neural networks. At the end,
Yes.
explain the sigmoid function like that. Madam has explained.
Right. Yeah. So one name for this is binary cross entropy loss. Right?
Yeah.
That's you use it.
Sir, then what is multi-class cross entropy loss, sir?
Yes, good. So I was coming to that. Multi-class classification, for example, let's say, right? So then so it's not called binary, it's just called cross entropy loss. Cross entropy loss. So, okay, but first, before that, how would you build a network to give you multi-class classification? Any thoughts?
Three output
Okay.
nodes, while output layer will have 3 nodes, say for 3-class problem. And
Okay.
and then sigmoid will give us the probability of that output being that uh, particular node, output node. So
Okay.
basically, uh, say the MNIST problem, we have 0 to 1, 0 to 9 as the output nodes, and each after the sigmoid function, the probability whether a picture is that 1 or 5 or 6 that will be given. That can be a neural networks classification, multi-classification problem.
Okay, got it. Okay, so we'll use a simple example. Let's say I have 3 classes classification. Okay, so let's say I have dog, cat, and monkey. Okay, I have an image and there's some network here, and finally at the end I have 3 nodes as you mentioned. Because why do I have 3 nodes? Because I want to know whether the probability belonging to dog or cat or monkey. That's what I want to do, right? And I want to train the model in such a way. Now, will it be enough to have sigmoid at these individual ones? Is that enough? Is there something else you need?
Sir, the probability of all the 3 should match it to 1.
Perfect. That's the problem, right?
Yeah, but it will not match to 1, not necessarily.
Not necessarily if you use only sigmoid individually, right? Because the idea, so the problem that we have at hand is I have an image, it belongs to one of these guys, one of dog, cat, or monkey. Fine. So see, this is the problem that we have at hand. So whatever I need the probability of all of them to be equal to 1. So we don't use sigmoid, we use a what you can say, a more higher version of sigmoid called as softmax function. Okay, so I'll tell you what softmax is. Softmax is basically, let's say this is node 1, 2, and 3. So the way softmax works is it will say e power, let's say output is node 1, right? So f1 of x divided by sigma of e power fi of x, I equal to 1 to 3. Right. So the probability that the image belongs to class 1 is taken as e power f1 of x divided by e power fi of x summation, right? And then class 2 will be this, class 3 will be similarly, use 2 here and 3 here, you will get this. So then when you add up the probabilities, you will get 1, because we are normalizing. Again, very trivial sort of solution, but we are normalizing across the whole sum. Therefore, you will always get a probability distribution over the 3 classes. And then you can choose, you can say, okay, whichever is the highest probability, I classify it to that class and so on. Is that clear?
Yeah, that we can do without E also, like directly.
Yes. Without E also is possible. This is the general convention that is used to make it. So, but see, but without E again, you have to be careful, because you cannot have these values becoming negative. Right. So E is sort of like I would say sort of like a very general purpose solution, where whenever you want some value which is strictly greater than.
Sigmoid function is always 0 to 1, right? Output.
No, you're right. You're right. So you can put sigmoid here, then you're safe. I'm saying in general, let's say if you were to use any random function, but be careful that it should always give you a positive value. Okay. Okay, so this is generally used in your softmax function is used to convert the outputs of this neural network into a probability distribution now over the 3 possible values. Now, so then coming back to the question.
Sir, so what you mentioned in your last sentence was, instead of softmax, we can even use sigmoid here, right? Since even sigmoid sometimes give the probability in some between 0 to 1, 0.5, 0.6 also is can be given.
And then pick up the highest.
You have to normalize it. That's the point. You have to normalize it. So
without normalizing also, if you pick up the highest sigmoid output, that will be giving you the same output as that softmax, right? That will, because
yeah, that is what I was also thinking, sir.
So the MNIST problem pay usually what it's pick up the highest, that is basically same as that whatever you are doing. After the sigmoid output, pick up highest sigmoid output.
True, sir. I also believe, since output of 1, 2, 3 are anyway between 0 and 1 output of sigmoid, so the highest of that should be the right choice.
Sir, can I clarify this one, sir? I think we require some clarity here. The first thing, when you're telling the class 1, like let's say dog, cat, and monkey. Suppose I am telling the class 1 is dog. That means I'm comparing dog with rest. The probability of that 0, 1 is basically dog with compare both cat and monkey.
Exactly. Yes, it will be against both.
So okay, then again with the other one, cat with others. So it's the one with others, correct?
Right. Yes. Yes.
And after that, yeah. You continue, sir. Yeah.
So let's say if you were to use sigmoid in individual ones, what will end up happening is when you're ready, let's say sigma 1 of x is the probability of belonging to, it being a dog versus it not being a dog. That's what we're trying to look at here. Okay.
Yeah.
Right. So this is what sigma 1 of x will give you. So it's not exactly probability of dog though. So probability of dog divided by, you will have to take the others. So because that's how you will.
Yeah. So that is like picking up the highest also.
It will come out to be this sort of form itself, because then again you can substitute your 1 by this e power and all of that. You will get something in this form. So at the end, softmax is that itself. But the point being that you need to normalize it so that it's a valid probability to be considered. That's the problem. Right. So see, you're correct on the point that, okay, if you use highest value, it's the same. But the point is, if you don't do this, it will not be a valid probability. That
Yeah,
will be
it
the
will not be probability. It's like probability of the dog being yes or no, basically. Each output node.
each output. Yes. Right. Yeah. So that's this one. And then coming to cross entropy loss. So very similar to the binary cross entropy loss. The idea is you take minus of again summation of all the classes. Let's say sigma I equal to 1 to 3. Then yi into log yi hat. So yi hat is basically the probability that it belongs to this particular class, right? So here again same idea. So here yi basically you're coding it as again is it belonging to the class that the sample belongs to and so on. Let's say you're talking about um, the sample belongs to dog, right? So then the particular y0 will be 1, remaining will be zeros. Okay, so then what will happen is you will have the loss function will turn out to be minus log y1 hat, right? And you're saying minimize this, which means maximizing the probability that it belongs. The model outputs the probability that belongs it to dog class. That's exactly what we want to do. That's the error signal that is being used. All right. Is that clear?
Sir, why we are saying here minimize it, sir? Like why should we, why is that minimum term coming here?
Minus.
No. So
Okay.
basically, when you say loss function, so loss means you're trying to minimize the loss. So that's the convention we take. So gradient descent, we say
Okay, got it.
right. So minimizing this is nothing but maximizing y1 hat. That's the intuition behind.
Okay. Log of yi hat is something like a loss function. Okay.
Yes.
Like a
So
error, right? Okay.
this whole thing minus of log y1 hat will turn out to be the effective loss function for a given class that you're working with.
Loss or error function. That's what basically here we tell loss. Correct. Both are same.
Yeah, correct. You can say that you can call it error function itself, error or loss. Both are valid, terms to be interchanged. Not a problem. Yeah, is that clear?
Yes, sir.
So with neural networks, you can do regression, you can do binary classification, you can do multi-class classification, and okay. So one thought, the sigmoid idea that you guys were mentioning. Let me. This comes into something like multi-label classification. So I'll give you intuition what I think. So let's say. I think it's called multi-label. So let's say you have a image, okay, and you need to classify it in two ways, okay. So let's say, does it contain a dog or not, okay, versus does it contain a grass or not. Okay, so in this case, how many output values do you need from the neural network? Two, right? So whatever we have here, two numbers will be used. Now, will you use softmax or will you use individual sigmoids?
This is individual sigmoids directly.
Individual sigmoids directly, right? Same problem that we thought here, right? So let's say here we just want to know whether it belongs to dog or not, and whether it has grass or not in the image, right? So, but here the problem was a bit different. Here we are saying the image we want to classify it into one of three classes, but here the image can belong to actually speaking, one of four classes. So dog and grass, okay, not dog and has a grass, right? And then dog and not grass, and then let's say not dog and not grass, whatever, right? So you can either solve it in this way, which is, for example, let's say all four possibilities, versus you can have two sigmoids which work independently for these two. So whenever you don't want to have some sort of like a some sort of hard constraint of this sort of one of multiple things, this sort of using individual sigmoids will make sense, right?
It is like combining two classifiers, right, sir?
Two classifiers, exactly.
Two,
Yes,
okay.
because we are trying to classify it into two different classification problems. But the idea being that okay, I can use one network itself. So basically, then it can capture any common features and etc. etc. All of that factors will come in. So this is one way of doing it, multi-level classification.
Okay.
Okay,
Okay.
I want to go to something very basic, which I get confused. In the single perceptron, we have inputs
Yeah.
x1, x2, x3, and the
Yeah.
weights w1, w2, w3.
Mm.
Okay, but we add a bias B,
Mm.
and the bias also is given a weight. Why do we add this bias for what? And who
Um,
and how do you and from where do you get this? I mean, from where this is not an input variable, isn't it?
no, not input variable. So okay, so this is basically saying like let's say you have x1, x2, and so on, xn, and as you said, w1, w2, wn. So now let's say the idea is, let's say you have +1 and this is the bias term. So the idea is, let's say if there is something which is common for the output, right? Something which shifts in its scale. For example, let's say I have a linear regression problem. Let's say we'll come to the very, very simple problem here. Let's say something like this. Okay, so the best fit line that is there for this is something like this, right? So now So now I want to be able to capture this shift that is there in this Y alone, right? So so this shift doesn't get affected by any of the X features, right? So if I don't model this, then what will happen is I am left to choose between these possible alternatives. Which alternatives?
Parallel lines. Parallel
Yes,
lines.
all which go only through origin, right? Only these I can choose. So
Okay.
then what will end up happening is I'll have to choose something like this, for example, say, okay, this is what I can do best. So the idea is it bias helps you to capture any factor that is there that is sort of not dependent upon X and gives you a linear scale, variant of your output. That's the reason we add bias
But the
in all.
bias is ought to be a constant, or bias can be a function.
No.
No,
So
no,
bias
it's C.
is
It's C. Y is equal to
bias
mx plus
also a
C. That's
parameter
C.
like W1, W2, Wn, like how we have these
Okay.
parameters, right, of any function. So bias is also a parameter, and this is also learnt over from your data. Because then how will you know how much shift is there?
Oh,
Only from
one question. One
go ahead.
question is bias like always taken input as +1 that no do we fix the weight or the input do we fix it or we keep both variable to the bias line there is +1 and BU taken
Right.
ma'am took weight as always 1 and then changed the bias input so
Input.
do,
Okay. Fine. So again, you can think of it in multiple different ways. The math won't change. But why I prefer this is because of the fact that, see, when I write bias here and I wrote 2+1 here, because we don't change the input in any way. We are not interested. We don't change we don't learn the input. We don't change the input in any way. That's what this +1 means. It
correct,
is
correct.
fixed. It is fixed.
Yeah, it's
I
weight
will learn
changing
the
with gradient
weights
descent.
with gradient descent and all of that ideas, right? So the idea is that this is something that is learnable, and therefore almost all the books that I have seen, at least, they say that this is like the weight given to a constant input of +1.
Sir, can you think another way?
Mm.
This one is
Let's
giving infinity to the dot product. When you do the multiplication with the vectors, this
Ah,
one will give you easy for you to the calculation. I mean, that is one reason, no? If X transport X, when you do this, no, W transport X,
right.
in that this is also W0 if you think. If the
Correct.
B, yeah, that is the reason one why you're giving the one there. So when you do
Yes.
multiply it,
Precisely. So you can view this as, let's say,
the
W
transport
bar
into,
transpose, let's say,
yeah,
X bar, where
exactly. Yes,
where W bar can be seen as 1 and then all your
yes,
W's
yes,
back
yes.
all
Yeah, yeah.
here. So sorry, B here, and X bar can be seen as 1 and then all your X1s to Xn's. Correct. Precisely.
Sir, one final confusion, this bias. The term bias, the way we use here in neural network, is anywhere related to the bias variance trade-off in linear regression?
No.
Yes, correct, right? Not at all related, right?
No.
We are talking about different context word bias.
Yes. There it's very different context. There the idea in bias variance trade-off, the point is we are looking at bias in terms of the hypothesis space itself, right? If I use a complex hypothesis space, complex hypothesis function versus simple, how it varies and all of that. This is not that. No.
So if the data is overfitting, then we say it is a low bias, correct?
Yes.
So in this neural networks, what you're saying is biases needs to be learned and the input to the bias is generally kept as +1.
Correct.
As a convention.
As a convention, correct.
Can I say something?
Go ahead.
Hello. Yeah. In neural networks context, the way I have seen this explained elsewhere with regard to Wx plus B, and I'm talking about for simplicity's sake, the scalar case where you have just one single input X, a neuron with a sigmoid activation and a single output. And if you're using sigmoid in that case, then you'd have 1 upon 1 plus e raised to minus x in the nominal case. No bias and no slope. Now, instead of x, if you put in Wx plus B over there, then what you're doing is that the sigmoid shape that you have, the W controls the slope of at which that neuron fires. That is the slope of that region where it goes from 0 to 1, or from 0 to 1. That is controlled by the choice of W. And the B controls at what point along the x-axis, at what x value you're going to get that neuron firing. So if you want to shift that sigmoid shape along like horizontally on your xy plane, then you choose the value of B accordingly, so that wherever B is, wherever x is equal to B, that's where you're going to get the sigmoid function value as 0.5. And then the W is going to control how close to a step function it is going to be, how fast it is going to fire. So according to this is the geometric sort of perspective on it. This is how you decide what value you want, and you are using these W and B as tuning parameters to fit the function so that your XY relationship is accurately represented when your training is done.
So you are saying that if B increases, that means your sigmoid function is going to shift to the right of the x-axis.
Yes, in the positive direction. Yes, you can try it. I mean, just
you put. And if W increases, I think what is going to happen is that the slope of the sigmoid function is going to become steeper and steeper.
Yes, you can just plug in a few numbers. You can in fact write one simple program and do vector input, vector output, and you will see and plot the graph. You will see this is exactly what's happening when you change W and B.
Okay, so that's a very interesting observation.
Something like this. So in this case, the W of the red one is actually
higher than W of the green.
W of the green one. Yeah. And
both will go 0 to 1. Both will go 0 to 1. Both the red and the green both have to go 0 to 1. There's an offset in this case.
Sorry, yeah. So it'll go something like this. Yeah, yes. You can imagine it. So
okay, one last question which I'm getting confused is
clarity for
why do you need a neural network? How is it used in regression and for what? I mean, there are so many simple methods of doing regression.
Okay, good, very good. So, okay, so I'll tell you one theorem which I have never been able to prove or understand, but I will tell you what it means. So there's something called as universal approximation theorem.
But I wanted to ask regarding it.
Sir, neural network is not only for linear, it is for non-linear also, general purpose.
No, but his point, once again, Krishna, so his point is valid because his point is, okay, I can use SVM also, no? SVM also is general purpose. So, but the point is this, in the universal approximation theorem, what this says, any neural network you take, so any function you take, for example, any function you take, I can have a neural network approximate this function to arbitrary closeness. What does arbitrary closeness mean in mathematical term? Is that whatever error you choose between the actual true minus your approximation we generally represent as a hat, right? So e minus f of it can be made as close to zero as possible, where say epsilon is some small value. Any for any possible value of sigma, epsilon you can use, and I can always get the error between the true and the approximation to a very close value. So therefore, so what does it mean overall? It means any true function is there, I'll be able to approximate it to a very good approximation. That's the reason. So we say, so therefore, let's say, so now the point is this, let's say in regression, the point is that there is a function which relates your input to output. Now, instead of trying out all of these different values different functions, methods that exist, I can use neural networks to learn this, to have an approximation of the true function to any arbitrary closeness. That's the reason neural networks are sort of preferred in some sense. That's the theorem. I don't know how to prove it. Go ahead.
Okay.
Sir, even mathematically, any continuous function can be approximated by Taylor series. So in the Taylor series, the coefficients are there. So those coefficients are maps to the neural network weights here. I don't know. I'm just intuitive understanding.
Yeah, good, very good. So Taylor series, the point is Taylor series is for, again, as you said, for well-behaved functions. Well-behaved is basically where they have good, where they have, what is it called? Nice gradients and all of that for multiple, all of that is there. So continuous and all of that. This doesn't make that assumptions if I'm not wrong on the true function. I'll have to check this, but yes, as far as I remember, it doesn't, I think. But yes, so this is the thing. So Taylor series is for well-behaved functions only, whereas this theorem tells you that neural networks can do it for any function in the world.
Can I comment here?
Go ahead.
Right. This universal approximation theorem, I've seen it in another, again, NPTEL course on deep learning specifically. And there, the way it was explained is that any continuous function can be approximated by a neural network that is one input layer, one output layer, and a single hidden layer where you can very allowed to have as many neurons as you want in the hidden layer. And the reason this works geometrically, they say, is that you require two of those neurons in the hidden layer to approximate what is called one tower function, which is and therefore and you approximate your let's say for the scalar case x and y, you have one graph on the 2D plane, one continuous curve, and you slice that vertically into long rectangles which are as close to thin lines as you want. Now for each one of those thin line-like rectangles, you require two neurons in the hidden layer. So now you slice it as much as you want, depending on the accuracy that you want to approximate it by. Geometrically, this whole proof is reminiscent of the way you go from the summation to integration approximation, the proof that we see in 12th standard. So this diagram looks exactly like that. And now it's simply a matter of slicing your curve, whatever arbitrary continuous infinitely differentiable curve that you have. It's about slicing it into as many rectangles as you want and then putting two neurons for each of those rectangles. And because you can draw any arbitrary curve, therefore you can put as many, I mean, no matter if you're allowed to have infinite neurons, then you can definitely approximate it. That is the way they explained it.
Right. So, yeah. So, feel free to, read about this more. Again, so I would say that this is what my level is on this particular theorem. So I don't know much details about this right now, right? But yes, thank you, SK, for the nice explanation. So I would encourage anyone who wants to go through it, please go through it. You'll get to know why this is such a important idea. Okay.
And the term firing a neuron, what gives me an intuition which is slightly, I think, is wrong. It seems that somebody is withholding, and only after it meets a trigger, the neuron gets an output is released. Is it true? But that may not be true if at all. It's if it is not what you call a nonlinear function, which is if you have f of x is equal to x and not a redo or a sigmoid, then such a thing, the question of firing doesn't arise, right? What is the meaning of the word firing the neuron?
Okay, so okay, so firing a neuron. This is taken actually from the idea of from the neuroscience concepts. So where the idea is that any neuron in the neuroscience terms, let's say, what happens is it needs some amount of potential to get activated, and then so once that potential is reached, right, let's say there's some potential access. Okay, so once the potential is reached, then it sort of fires like this. So it basically communicates that information to the next neuron. This is the idea. This is the parlance of the neuroscience community. Here that doesn't really apply, because the idea is whatever, let's say, sigmoid function you use for your, what do you call that, activation function, right? So whatever you do, it's still going to give you an output at the end of the day. That's not true with these neurons, at least to a first approximation.
Unless you
So
have a very negative bias.
I'm sorry.
Unless you have a negative bias.
Unless you have a very negative, yeah, exactly, yes. So whatever at the end this output, so your sigma of wi xi plus b, whatever you have this, right, for every neuron in neuron of artificial neural networks. So here the idea is whatever you have, it'll based upon whatever sigmoid computes, it's just going to give you some output. Now you can define things saying, okay, it is firing only if this value is above 0.9 or 0.99, then I consider it to be fired. If it's less than 0.01, I consider it to be not fired. But those are all again not clearly defined, so don't worry about it.
Sir, my intuitive understanding is it is exactly the firing or activation which actually gives a nonlinear behavior to neural network. Otherwise, if there is no that concept, the whole neural network can be mathematically proven as a linear approximation only.
No. So correct. So I mean, so the way these neurons work, at least to a first approximation, is yes, they are nonlinear functions. That is the sort of parallel between artificial neural networks and the brain neural networks that we have. But that's all I would take. I wouldn't see too much into it. Yeah. Okay. I mean, so I just wanted to cover one topic which somebody had actually asked me to cover. So autoencoders. See, autoencoders. See, I'll give you one basic idea is that these are the networks which take, let's say, some input data, and generally what they try to do is they try to compress them into a lower dimensional space, and then again reconstruct them back, right? So let's say this is the input is x, output is x hat, and you try to make x as equal to x hat. Now I'll give you one sort of intuition why this is required or good or whatever. So let's say you have a image and you have a dog and you have a frisbee somewhere here, and you have some grass and all of that. So let's say if I ask you to describe this figure, right? So if I just tell you, okay, there is a dog, there is a frisbee, there is some grass, that's enough. If you want to be more precise, I can say, okay, the dog is on the left side, right side of the image, frisbee is in the bottom corner, everywhere else there is grass. That's another level of detailing that you will get. I'll say, okay, no, I want some more details. So I'll say, okay, the dog's breed I will tell. Let's say I can also say, for example, let's say the dog's tongue was out or not out. What is the frisbee color? What is the frisbee's orientation? Grass, for example, let's say it's more green here or less green here or more dark here, etc. So the idea is, let's say whatever input you have, some x, you can compress it to whatever level of information you want to keep, such that it's able to again get back the true value back. That's the idea in autoencoders. Now, this is exactly the idea even in PCA also, if you remember. In PCA, the point is you're trying to capture as many dimensions of variations as possible, and then you look at how much of the variance is already explained. Now, so where you stop in PCA is, for example, let's say you will say, okay, I will use the number of principal components which capture, let's say, 90% of variance, or 80% of variance, or whatever. So there the idea is you are willing to lose some detailing of the information, but such that your the amount of dimensions that you get at the end is lower. So you might be able to work with whatever data you whatever algorithm that you have at hand. Same idea with autoencoders. The idea is you're trying to reduce the dimensions into some lower dimension, such that you're able to reconstruct the image back to whatever level of detail you want to be able to whatever detail you want to do. Now the question is, how do you train it? This is exactly where we use the idea of neural networks. So you have all these weights here, all these weights here, and you take some sort of error function between these two. If it's images, people generally use either, again, MSE, or there are some other complex things people have tried. So you can use that to train these networks. One very trivial solution, as somebody can as one can imagine, is that I can just keep the same X here, right? Keep the same X here. I'll say, okay, whatever I got, copy it here, and then I'll be able to minimize my MSE, right? Let's say MSE will now be 0 because all the detail was here. But we don't allow that by these factors. We say, okay, it has to be lower dimension, or for example, let's say the whatever function I have here, it cannot be, let's say, the I function, that is I of X equal to X. This function cannot be learned here. Those sort of things are generally done to make sure that this is not this doesn't happen when you use a autoencoder. Now, one idea which ma'am has told in the lectures is that this allows you to not have this vanishing gradient problem, the gradient getting diffused or whatever. The idea here is, because these weights are now capturing some information about X, right? They're able to capture some information about X. So starting from a random weight maybe starting from these weights may be more beneficial than starting from a random weight and training the whole network from scratch. That's the idea. Again, I'm not really sure how that helps in gradient diffusion problem. I can ask the other TAs to comment on it. But I hope you got the idea of autoencoders. Is this clear? Any doubts on this particular point?
Yeah, but what is its practical use?
Yes, again, so same use of PCA, right? So you want to use a dimensionality. That's the main idea. Yeah.
Sir, for example, in JPEG or MPEG image decoding, actually it is actually reducing the amount of data, right? That's also, you can say, as a kind of autoencoder. JPEG,
so autoencoders are basically, these are learnt over specific data. In JPEG and all of that, that's basically it's a known function, right? You apply that function, you will get the same thing. Again, this goes back to the idea of machine learning. In machine, the idea is what you want to learn a program. You want to develop a program, right? So from the data and from the target and whatever, right? Whereas those compression, it depends on what data is there at hand. Like, is that data even good enough so that we can compress it or not? For example, those things will come into picture. Yeah. Is that clear? And one thing to people who are interested in more of this, you might want to read up something called as manifold hypothesis. So, and as the name suggests, it's a hypothesis. It has not been proven yet. But the idea is that whatever the real world data that we have, let's say images, speech, text, all of them, they actually, we don't need whatever the amount of dimension that we're using currently to represent them. We don't need that high dimension. If you reduce the dimensions, you will still be able to capture all the information that those images or text or speech signals have. And that's where these sort of ideas come into picture. What is that low dimensional space? What is that low dimensional representation of those inputs, which can still capture all of the information about the input, and thus those will help you work with more ML algorithms which work better in low dimensional spaces. All right. Okay, so we'll close here. If you have any last questions, we can take them.
Okay, what is your
does it
email?
I'm sorry.
What's your email? I forget.
Email is rajv@iic.ac.in.
At iic.ac.in. Okay.
Yeah. Okay, next
Sir,
somebody
one
else.
last question regarding this. When we use autoencoders for the inputs, we need not know any labels and all, right, sir? So it is just taking some unknown data and just reducing the dimension and again trying to get it back.
Correct. Just like PCA. So it is also an unsupervised learning, way of learning, just like PCA.
Okay.
PCA also doesn't contain labels, right? So it's just unsupervised.
Okay. Okay. Okay.
Sir, excuse me. Sir, in autoencode, as you said, it is going to reduce the dimension and finally is going to get back the original dimension as it is, or based on the requirement, it can be extracted.
So based on the requirement, for example, so that is basically that requirement is quantified in terms of how much error is there in the reconstruction. So we're saying we're doing reconstruction here, right? Because we're saying whatever is there X, go to some space and get it back. So that is the reconstruction. So construct it again. That is through this bottleneck that we have, this low dimensional space. So let's say if you get like a MSE of, let's say 0.1, if you're happy with it, go with it, no problem. If you want even lower MSE, then either you have to make this network more complex so you can capture more complex patterns, or you might have to increase your number of dimensionality, because it could be that more number of dimensions are required to explain the current input that you have. So all of those things, you have to try. These are all empirical ways of solving. We don't have really good handle on that yet. So that's the point. So how well it reconstructs, based upon whatever tolerance level you have, which is again a personal and something that the problem statement has to define. Based on that, you will then learn your representation. And then what you will do is you will use this part of the network. So only the first part of the network you will use. Whatever X you get from during your test time, you will pass it through this particular part of the network. Whatever output comes from this middle layer, you will use that in your ML algorithm, which you have developed on this lower dimensional space. That's the overall framework that generally we use autoencoders with.
Sir, can you repeat that last sentence, sir? What you have mentioned?
Yeah. So let's say you learned an autoencoder, right? You already learned that. So you're using some training data, and you on that same training data, you applied this the autoencoder on this part of the network. So whatever output comes from here, you will use those outputs as your training examples for some ML algorithm, right? And you'll train some ML algorithm. For example, let's say some classification problem, right? Then on your test time, what you will do, you will pass the test X through this. Whatever output comes from here, you will use that to on your ML algorithm. Whatever ML algorithm now gives the output as your, let's say, Y, for example, that will be your final value for this X that you had, a high dimensional X that you had. That's the
okay.
general.
Okay, so in that autoencoder diagram, whatever you're having is that output is just used to verify or to train that autoencoder. But after that, only the reduced dimensions of features would be used for the classification.
Correct. Yes.
Okay.
Correct.
Okay.
Yeah. So again, see, I mean, that's a general framework. People have tried to use this part of the network. So actually speaking, okay, we are. Yeah.
Because in the class when ma'am was explaining, it was like she was cascading this. So I was a little confused. So she was like X bar again was giving the input to next hidden layer. So at least I think that is what I have understood.
Okay, it's not
in the class.
But okay, but yeah, so this is generally the way we use. This is called the encoder part of the network until this part, and this is called the encoder part of the network. So you have encoded X in this lower dimensional space. You decode the X from this lower dimensional space. So people have tried to look at how to. I mean, there are different uses of this decoder also. The general way of using autoencoders is you do this. You keep this encoder part of the network. whatever output comes from this particular layer of this, this network, that is then used for your ML, some downstream task. That's the idea.
Okay, got it, sir.
Yeah. Okay, guys, I think we'll close. Any
Sir,
last?
Sir, my query, sir. Hello.
Go ahead. Yeah, Jitendra, go ahead.
Yeah, question number 3, sir. Actually, hard margin is for 0 error, and 0 is not low. I think low we define for a little tolerance we allowed there. That's why the picture zeta come, no? Slack variables.
Right.
But so I put it a D option, sir. But answer is A. They taking 0 as a low means soft margin and hard margin. How is they defined? Hard, I think 0 error, right? Exactly 0.
Which was it?
We don't allow noise.
Yeah. So yeah, I told about this that very low in the sense 0 is what you can understand.
No, how, sir? 0 is different. 0 means we have not no any tolerance. 0 means there is absence of tolerance. But that's the zeta is coming to the picture. No? Low means low tolerance we can handle. Otherwise we cannot infinite value of tolerance. We cannot in SVM we can handle.
Right.
So what is the role of zeta? That's a few points are here and there. That's the low tolerance, like beyond the boundary, that outliers point you can say.
Right. Okay.
So that's why the correct answer should be D. So that's hard margin and soft margin clearly defined, right, sir?
I get your point, Jitendra. I get your point.
Yes, okay.
Yeah. So let me ask them here. Matlab, see.
Okay. Actually, there is conceptually, if it is incorrect, then that's fine, sir. It's help us to learn us, but language-wise, a little confusing.
I understand. See, we can quibble over the terminology for as long as you want, but yes. So let me ask them. But I hope that all of you have understood the spirit behind the
concept. I got, sir. Just the value hard word, and that's all. That's it only. Okay, sir. Thank you.
Okay. Okay, guys. So we'll see you next Saturday. Yeah.
Thank you, sir. So, yeah, this session was very helpful.
Thank you.
Thank
very
you.
long and a very interesting session. Thanks for your patience.
Yeah.
Great interacting with you.
Yeah. Thank you.